Welcome to lecture 7 on trigonometric functions. In the last lecture, we had discussed trigonometric equations. We gave general solutions to trigonometric equations of the form sin x equal to sin y, cos x equal to cos y, and tan x equal to tan y, and we solved a few problems. So, in this lecture also we are going to continue solving problems. Let us first start with a quick recap of what we did in the last class. So, we discussed general solutions of trigonometric equations of this form sin x equal to sin y, and we said that the solution to this equation is x equal to n pi plus minus 1 to the power of n times y, where n is an integer. Similarly, for the trigonometric equation of the form cos x equal to cos y, we showed that the general solution is of the form. So, here when I say x equal to, it basically means that x belongs to this set. So, this is the general solution set for this equation, and for cos x equal to cos y, x belongs to the set 2 and pi plus minus y for all integers n, and for the equation tan x equal to tan y, we showed that the general solution set was of the form n pi plus y for integer n. So, let us continue solving some more problems. So, in this problem we are asked to find the general solution to the equation cosecant of x equals cotangent of x plus root 3. So, one technique of solving problems where you get cosecant and cotangent is to express them in terms of sine, cos and tan, and then use the all the identities for sine, cos and tan in solving this equation. So, we know that cosecant of x is 1 over sine x equals, we can write cotangent of x as cosecant of x over sine x plus square root of 3, and then we bring this term on the left hand side because we see that 1 minus cos x is something that we know that 1 minus cos x is equal to 2 sine square x by 2. So, we will try to use that. So, then this becomes, or so that is one way, or the other way is that we multiply both sides by sine x, and then we get 1 equals cosine of x plus root 3 times sine x. So, this probably is of the form a cos x plus b sine x, and then we had discussed in one of the previous lectures how to simplify that. So, this can be written as 2 times half into cos x plus root 3 over 2 into sine x, which can be further written as, now here we know that we can replace half with cos of 60 degrees and root 3 by 2 with sine of 60 degrees, or we can even do it otherwise. We can even write root 3 by 2 as cos of 30 degrees and half as sine of 30 degrees, as sine of pi by 6 into cos x plus cos pi by 6 into sine x, and this is of the form sin A cos B plus cos A sin B. So, this thing inside the braces is sine of x plus pi by 6, 2 times sine of x plus pi over 6. So, we on the previous slide we reduced that 2 into sine x plus pi over 6 is equal to 1, or sine of x plus pi over 6 is half, but half is the same as sine of 30 degrees, which is pi over 6. So, here we again have an equation of the form sine x is equal to sine y, and for this we know that the general solution is that x plus pi by 6 should belong to the set n pi plus minus 1 to the power of n times y. In this case y is pi by 6. So, pi by 6 for all integer n, and which is the same as saying that x belongs to the set n pi plus minus 1 to the power of n pi by 6 minus pi over 6, and belonging to integers. So, this is the general solution set for the equation cosecant of x equals cotangent of x plus square root of 3. Let us take a slightly more difficult problem. So, in this problem we are asked to find all the solutions to cosecant theta plus secant of theta equals 1. So, as again we will express cosec theta as 1 over sin theta plus this will be 1 over cos theta equals 1, and then when you multiply both sides with sin theta cos theta, you end up getting cos theta plus sin theta equals sin theta into cos theta. But this does not appear to be, well, this appears to be of the form a cos theta plus b sin theta, but then here we have a product of sin theta cos theta. Here there are many possible ways of doing this problem. One possible way is that using the fact that sin square theta plus cos square theta is 1, what we can do is we can define t to be sin theta plus cos theta, and then if you, so this is a defined new variable that is defined here, and then you will see that t square is sin square theta plus cos square theta plus 2 sin theta cos theta. So, but sin square theta plus cos square theta is 1, and therefore, t square is 1 plus 2 sin theta into cos theta. And from here we can see that sin theta into cos theta is actually equal to t square minus 1 over 2. So, now if we see, go back to the trigonometric equation, the left hand side was t is equal to, the right hand side is t square minus 1 over 2, and t has been defined to be sin theta plus cos theta. So, the equation in terms of t then becomes t square minus 1 is 2t, or t square minus 2t minus 1 equals 0, and therefore, since this is a quadratic equation in t, there are two possible roots. The roots are 2 plus minus square root of 8 by 2, which is equal to 1 plus minus square root of 2. Now, we know that t is equal to sin theta plus cos theta, which can actually be written as square root of 2 into sin theta times 1 over root 2 plus cos theta times 1 over root 2, which is equal to, now we know that 1 over root 2 is cos pi by 4, and it is also equal to sin pi by 4. So, we can write here cos pi by 4 plus cos theta into sin pi over 4. This is again of the form sin A cos B plus cos A sin B, and therefore, this expression inside the braces is sin of theta plus pi by 4. So, this is equal to sin of theta plus pi by 4, and therefore, from here we know that the magnitude of t can, since the value of sine is between minus 1 and plus 1, the absolute value of t has to be less than or equal to square root of 2. If we go back to the roots of this equation, if we take the root which is 1 plus root 2, that is not a feasible solution, because t is sin theta plus cos theta, which is equal to this, from where we had seen that the absolute value should be less than root 2. So, we cannot take the root which is 1 plus root 2, because that is outside this, that does not satisfy this constraint. So, therefore, the only other solution is that t is equal to 1 minus root 2, and we already have this simplification here. So, ultimately we end up with t equal to root 2 into sine of theta plus pi by 4 equals. So, we only take the other the root which is satisfying this constraint, which is 1 minus square root of 2. So, this whole thing can be again rewritten as root 2 into sine of theta plus pi by 4 equals 1 minus square root of 2, which implies that sine of theta plus pi by 4 equals 1 over root 2 minus 1. And let this be equal to sine of some angle phi, because this value in the braces is between minus 1 and plus 1. So, we can always find a value for this angle phi between 0 and 2 pi, such that sine of phi is equal to this value. So, let phi be that value. So, now we again have the same equation of the form sin x is equal to sine of y, for which we have the solution that theta plus phi by 4 should belong to the set, and pi plus minus 1 to the power of n times phi for all integer n, and therefore, the solution set, the general solution set for theta will be n pi plus minus 1 to the power of n times phi minus pi by 4 for all integer n. So, if you go back to the solution to this problem, we used a little trick here, because on one side we had the sum of cos and sine, on the other side we had the product. So, that is why we had to use this trick, and we use the fact that sin square theta plus cos square theta is 1. So here is the next problem. So it is asking us to find the general solution to this trigonometric equation. And again, what we can do here is that we can write this as 1 plus 1 over cos of 2 theta into 1 plus 1 over cos of 4 theta is equal to cos theta over sin theta. And then we multiply both the left hand side and the right hand side by, so we multiply LHS and the right hand side by cos 2 theta times cos 4 theta times sin theta. So what we end up getting is 1 plus cos 2 theta into 1 plus cos 4 theta times sin theta equals cos theta into cos 2 theta into cos 4 theta. This whole thing will be equal to 2 cos square theta, and this other expression will be equal to 2 cos square 2 theta times sin theta equals cos theta cos 2 theta cos 4 theta. And then taking whatever is on the right hand side, bringing everything to the left hand side, we get zero. And we see that there are some common terms in both these terms, so we factor them out. So what we get at the end is cos theta is a common term here, cos 2 theta is also common. So we take both of them out, and then we have equals 0. And here we see a pattern that 2 sin theta cos theta is in fact equal to sin 2 theta. So using that fact, we have 2 sin 2 theta into cos 2 theta minus cos 4 theta. And again we see the same pattern with 2 theta. So this thing is now sin 4 theta. So now this equation is 0 if and only if either cos theta is 0 or cos of 2 theta is equal to 0 or sin 4 theta minus cos 4 theta equals 0, either of these three. We need to find the solution set for each of these three different equations and take the union of all of them. So of course we know that cos theta equal to 0 means that theta belongs to the set, because this is of the form cos theta equal to cos pi by 2, and then we can use the general solution to equations of the form cos x equal to cos y. So the solution to this is 2n plus minus 1 into pi over 2, where n is an integer. Then for this equation, cos 2 theta equal to 0, the general solution is that theta belongs to. So, it is going to be exactly the same, except that because we have a 2 theta here, we will have it as 2n plus minus 1 into pi over 4 for all integer n. Now, for this last equation, which is this can again be written, this actually implies and is implied by the other this equation, where so even if I multiply with 1 over root 2, the right hand side is still 0. Equals 0, and this can then be written as into cos, because cos pi by 4 is equal to sin pi by 4 is equal to 1 over root 2. Which further implies and is now this is the left hand side here is of the form sin A cos B minus cos A sin B, which is sin of A minus B. Therefore, this left hand side is equal to sin of 4 theta minus pi by 4 equals 0, which implies and is implied by the fact that 4 theta minus pi by 4 must belong to the set n pi for all integer n. So, here we are using the formula that of sin x equal to sin y with y equal to 0, and this then implies that theta belongs to, we move the pi by 4 inside the set, n pi over 4 plus pi over 16, n being integers. So, the final solution to the problem, the general solution to the problem 1 plus sec theta into 1 plus sec 4 theta equal to cot theta. So, the general solution is given by the union of these sets 2n plus minus 1 times pi by 2 all integer n union with 2n plus minus 1 times pi over 4 again integer n union with n pi over 4 plus pi over 16 integer n. So, this is the final solution set for this trigonometric equation. So, let us consider another problem. So, in this problem we are asked to find the smallest positive value of x such that this trigonometric equation is satisfied. So, as again we write tan x as sin x by cos x, and therefore, this becomes sin of x plus 100 degrees upon cos of x plus 100 is equal to sin of x plus 50. So, I am not writing degrees in the interest of time, into sin of x into sin of x minus 50 divided by cos of x plus 50 cos x into cos of x minus 50, and then we multiply both sides. So, multiply LHS, and the right hand side by cos of x plus 100 times cos of x plus 50 times cos x times cos of x minus 50. And then after this multiplication, what we end up getting is sin x plus 100 times cos x plus 50 times cos x times cos of x minus 50 equals sin x plus 50 times sin x times sin x minus 50 times cos of x plus 100. We see that on both the left hand side and on the right hand side we have products of sine and cosine. But now the question is, should we combine this with this, or should we combine sine of x plus 100 with cos x? And what we see is that if we combine sine of x plus 100 with cos x, then we get a term which is sine of 100, and we get a similar term if we combine cos x plus 50 with cos x minus 50. And something like that will also happen on this side if we combine sin x plus 50 with sin x minus 50 and cos x plus 100 with sin x. So let us try to do that and see what happens. So we start with simplifying the left hand side first, and of course we can multiply both sides by 4. So we need this 4 because we will try to recall the expansion for 2 sin A sin B, 2 sin A cos B, and 2 cos A cos B, and 2 cos A sin B. So on the left hand side what we can write it as 2 sin x plus 100 times cos x multiplied by 2 cos x plus 50 times cos of x minus 50. Now we know that 2 sin A cos B is sin of A plus B plus sin of A minus B, which is 100 degrees. So this is the first, this term on the left hand side, and then here we see the pattern for 2 cos A cos B, and we know that 2 cos A cos B is cos A plus B plus cos A minus B. So this term becomes, so this multiplied by cos A plus B will be cos 2x plus cos A minus B is going to be cos of 100, and then of course we can write all the 4 terms here very nicely. Plus sine of plus 100 times cos of 100 plus sine of 100 times cos of 2x plus sine of 100 times cos of 100. And we try to do a similar thing for the right hand side now. So on the right hand side we had 4 into sine x plus 50 times sine x times sine of x minus 50 times cos of x plus 100, and here we will combine sin x plus 50 with sin x minus 50 and sin x with cos x plus 100. So it becomes 2 sin x plus 50 into sin x minus 50 times 2 sin x cos x plus 100. Now, this is of the form 2 sin A sin B, which is equal to cos of A minus B minus cos of A plus B. So, cos of A minus B will be cos of 100 degrees minus cos of A plus B will be 2x. So, this is A and this is B. So, A plus B is going to be 2x multiplied by 2 sin A cos B for this other term. 2 sin A cos B is sin A plus B plus sin A minus B. So, sin A plus B is going to give us sin of 2x plus 100, and sin of A minus B is going to give us sin of minus 100, which is minus of sin of 100. And then we again write up all the 4 terms that we get. We end up getting sines of 2x plus 100 times cos 100. So, this is this with this minus sin 100 into cos 100 minus cos 2x sin 2x plus 100 plus cos 2x into sin 100. So, this is the right hand side and this is equal to the left hand side, which is sin of 2x plus 100 times cos of 2x plus sin of 2x plus 100 times cos of 100 plus sin of 100 times cos 2x plus sin 100 cos 100. And we can see that a few terms are going to get cancelled here, because this term will sin 2x plus 100 times cos 100 is both here and here. So, this gets cancelled out, and then cos 2x times sin 100 is also on both the left hand side and the right hand side. So, this also gets cancelled. So, what remains in the end is that 2 sin 2x plus 100 into cos 2x, which is essentially this term, bringing it on this side, and then plus 2 sin 100 cos 100 equals 0, which can be further simplified as, so from the previous slide we have 2 into sin of 2x plus 100 times cos of 2x plus 2 sin 100 cos 100 equals 0. Now, this is of the form 2 sin A cos B. So, we know that 2 sin A cos B is sin A plus B plus sin A minus B. So, this becomes sin of, so A plus B will give you 4x plus 100, and sin A minus B is going to give us sin of 100 plus, and this is, if you see the pattern here, this is sin of 200. This is of the form 2 sin A cos A. So, 2 sin A cos A is sin 2A, which is sin of 200, equals 0. And then here we will try to use the sin A plus sin B formula. So, this thing will become 2 into sin, so A plus B by 2 is 150 degrees into cos of A minus B by 2 will be 50 degrees. But sin of 150 is the same as sin of 30 degrees. so which is half. So this is equal to half. So 2 multiplied by half is 1. Therefore, what we have is sine of 4x plus 100 is equal to minus of cos of 50 degrees, which is minus of sine of 40 degrees, because cos of 50 is the same as sine of 40, which can also be written as sine of minus 40 degrees. So again we have the form sine x equal to sine y, for which the general solution will be given by 4x plus 100 belongs to this set n pi plus minus 1 to the power of n times minus 40, because y is minus, well here we should not, because we are using pi here and we are expressing the answer in terms of radians, we need to convert this back to radians. So this is not correct. So since this is degrees, so from degrees, if you remember one of the previous lectures, we just need to multiply this with pi over 180. So that will convert it back to radians. But then the same thing has to be done with this 100 also here. So in any case, this statement is correct. So for all n belonging to z, and then we can write that 4x belongs to n pi plus minus 1 to the power of n times minus, so this 40, we can simplify this as 2 pi by 9, and then we have to put a minus 100 over here, but minus 100, this is in degrees, so in terms of radians that will be minus 5 pi over 9, and again belonging to integers. And but this is 4x, so then we have to divide everything here with by 4. So what we end up getting is that the solution set is of the form x belongs to n pi over 4 plus, we can actually bring the minus outside, but into minus pi over 18 minus 5 pi over 36 for all n belonging to set of integers. So this is the general solution to this problem. And you can in fact find out the first, for example, if you put n equal to 1 for example, then that corresponds to the solution pi by 4 and then minus pi by 18 minus 5 pi by 36, which is pi by 4 plus pi by 18 minus 5 pi by 36, which in degrees is, this is 45 degrees, this is 10 degrees, and this is pi is 180, so this is 25 degrees. So this is equal to 30 degrees or pi by 6. So this is with n equal to 1, and then you put different values of n, you get all the general solution, all the solutions to this equation. Here is another interesting problem where we are asked to show that for all x in the interval 0 to pi by 2, this statement is true. Cos of sin x is always greater than or equal to sine of cos x for all x in the interval 0 to pi by 2. So for this, it seems that we need to use the identity that sine of pi by 2 minus x is equal to cos x, and a similar identity for cos. So, we can start with sine. So, this term on the left hand side can be written as sine of pi by 2 minus sine x, because cos theta is equal to sine of pi by 2 minus theta. So, if you want to show this, it is equivalent to show that this is greater than equal to sine of cos x. Now, remember it is said that x has to belong to the interval 0 to pi by 2. So, when x belongs to the interval 0 to pi by 2, let us examine the relation between pi by 2 minus sine x and cos x. So, let us examine these two terms for when x belongs to 0 to pi by 2. Of course, when x belongs to 0 to pi by 2, cos x will be between. So, at x equal to 0 it will be 1, and at x equal to pi by 2 it is 0. So, it is going to be between 0 and 1, and pi by 2 minus sine x at x equal to 0, this will be pi by 2, and at x equal to pi by 2 it will be equal to pi by 2 minus 1. So, it is going to vary between pi by 2 minus 1 to pi by 2, and we see that this interval as well as this interval, both of them are subset of the interval 0 to pi by 2. For example, this interval is a subset of 0 to pi by 2. The interval, the set of all values taken by cos x are also between 0 and 1 is also a subset of the interval 0 to pi by 2. So, this tells us that both pi by 2 minus sine x and cos x, which are the arguments here, belong to the interval 0 to pi by 2. So, essentially we have something of the form sine of A and sine of B. So, A is equal to, let us say, pi by 2 minus sine x, and B is cos x, and we are asked to show that sine A is greater than or equal to sine B, and we know that both A and B, so both A and B will belong to the interval 0 to pi by 2. If you would have seen the graph of the sine function, we know that, so I'll quickly plot the graph of the sine function. So if this is 0 and let us say this is pi by 2, so this is x and this is y equal to sine x. So at x equal to 0, sine x is 0, and then between 0 and pi by 2 it is monotonically increasing from 0 all the way till 1. So what that means is that for any two values, let us say A and B, if A is greater than or equal to B, as is the case shown in this graph, then sine of A, which is this value over here, so this value here is sine of A, will be greater than or equal to sine of B. So, sine of B is the, so this value is sine of B. So, A greater than or equal to B implies and is implied by the fact that sine A is greater than or equal to sine B. So, if we have to show that sine of A is greater than or equal to sine B, it only suffices to show that A is greater than or equal to B in this interval. Here, if you recall, A was pi by 2 minus sine x and B was cos of x. So, as long as if we can show this statement, if this holds true in the interval x belonging to 0 to pi by 2. So, x belongs to 0 to pi by 2, as long as we can show this, that will solve the problem, right. So, let us try to again further examine this particular equation. Showing this is equivalent to showing that cos of x plus sine of x is less than or equal to pi by 2 for all x in the interval 0 to pi by 2, for all x in the interval. So, we try to show this on the next slide. So, these two are again equivalent statements. Now, sin x plus cos x is equal to root 2 times 1 over root 2 sin x plus 1 over root 2 cosine of x, which is equal to, so again we can write 1 over root 2 as cos of pi by 4 and the 1 over root 2 here as sin pi by 4. Therefore, this whole thing simplifies to sin of x plus pi by 4. But then we know that this value, so when x belongs to 0 to pi by 2, x plus, it is of course, well, there is nothing much to see now, because the value of sin of x plus pi by 4 for any x, it has to be less than or equal to 1, and therefore, sin x plus cos x from this equality here has to be less than or equal to root 2. Since root 2 is less than, strictly less than pi by 2, it is easy to now see that, because root 2 is 1.41 something and pi by 2 is 1.57 something. From these two statements, it follows that sin x plus cos x is less than pi by 2 for all x belonging to the interval 0 to pi by 2. Okay, let us take another problem. In this problem, we have to find the smallest positive number p for which this trigonometric equation is satisfied, and in fact, the number p should be such that this equation has a solution x in the interval 0 to 2 pi. So, here again we use the identity that cos of theta is sin of pi by 2 minus theta. So, we write this left hand side as sin of pi by 2 minus p sin x equals to sin of p cos x, and this is again of the form sin x equal to sin y. So, for this to be true, it must hold that pi by 2 minus p sin x should be equal to n pi plus minus 1 to the power of n times p cos x for some integer n, for some integer n. So, let us now try different possibilities for this integer n and see what we get. So, if we try n equal to 0, for example, then the equation that we get is pi by 2 minus p sin x equals p cos x, which can be written as p into sin x plus cos x equals pi over 2, and then the sin x plus cos x can be simplified as p root 2 into, and then we again write it as 1 by root 2 sin x plus 1 by root 2 cos x, which is equal to sin of x plus pi by 4 is equal to pi over 2. Now, we are in the question, it is asked to find the smallest positive number p, but for p to be positive, we have to choose x such that sin of x plus pi by 4 is also positive, because pi by 2 is positive and root 2 is positive. Plus, since we want to find the smallest p, we should try to choose x such that sin of x plus pi by 4 is the largest possible positive value, which we know is 1. So, when this is equal to 1, we get the smallest possible value of p, which will be equal to pi by 2 over root 2. But this is only for n equal to 0. We can try for with n equal to 1. If we put n equal to 1, then we end up getting 2 minus p sine x equals pi minus p cos x. And what we, if we rearrange this, then what we end up getting is that p times cos x minus sin x is equal to pi over 2. And even here we can again write it as p into square root of 2 times, and then it will be cos x into 1 by root 2 minus 1 by root 2 sin x, which can be written as cos of x plus pi over 4 is pi over 2. But even here the largest possible of cos of x plus pi over 4 is still 1, and therefore the smallest positive value of p will still be the same value. And we can try like this for negative n also, and we will end up, in general what we can see is that this equation for a general n will only get satisfied if, so this can be written as minus 1 to the power of n plus 1 if I bring this, or sorry, rather it will be easier to take sin x on this side, so it becomes p into minus 1 to the power of n cos x plus sin x equals minus of pi over 2 into 2n, that is because of this term, minus 1. But one thing that is to be realized here is that if we then further write it as, we take the root 2 outside and then we bring the root 2 inside here, and if we see here, if we take the absolute values on both the left hand side and the right hand side, what we will see is that, so p anyways we want it to be positive, so mod p into square root of 2 into, now the absolute value of this thing inside the braces, this particular term, the largest possible value is still 1, because this particular term, no matter what the value of n is, this will always be less than or equal to 1. So the largest possible value is 1, and that should be equal to pi by 2 into absolute value of 2n minus 1. So from here it is now easy to see that for n equal to 0 we get this thing equal to pi by 2, n equal to 1 also we get this thing equal to pi by 2, but if we try n equal to minus 1, then we have 3 pi by 2 here. Similarly, if we try n equal to minus 2 or n equal to 2 or larger values of n, then we'll not get pi by 2, we'll get bigger numbers. But since we have to find the smallest positive value of p, we have to therefore choose either n equal to 0 or n equal to 1, for which the smallest positive value comes out to be p equal to pi by 2 root 2. And that finishes the solution to this problem. So with this we end this lecture on solving problems for trigonometric equations. In the next lecture we are going to start a new topic, which is inverses of trigonometric functions. Till then, thank you.